a function, we're going to try and connect these things together. If we have the graph of a function and its derivative together on the same graph, we want to try and make some connections between the two, because they are very much connected to each other. So I want to stick with this example right here, and I want to take a look at its graph. What does x squared look like? Parabola opens up, right? So let's start with the graph of f. I'm going to try and do this pretty accurate. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6. So at 1, it's 1. At 2, it's... At 3, it's off the chart. So it looks something like this. Everyone agree that's f of x? That's f of x. What does its derivative look like? Well, 2x, right? Let's plot that. Where does it start? Right here, and then up 2 to the right 1, then up 2 to the right 1. So it should be that line right through there. Okay with that? So something like this. That right there is f prime x. Jeez. All right, heads up back there. Ramiro? Heads up. It's coming to the trash can. Ah, hey, hey, hey. It's harder than that looks. What's the connection between these two graphs? Well, this is a secant line, but think about what did this thing represent? What did that represent? The derivative was always the what? The slope of the tangent line at a or at a certain point, right? So this is the function. This is the slope of the tangent line at that point. So what I'm going to do now is I'm going to walk out here to, let me pick a point. Somebody give me a point on the x-axis. Something either, what, 0, 1, 2, 3, negative 1? 0, well, hold on. Let me do negative 1, okay? I'm going to pick an x value of negative 1. I'm going to go to the original function. What's the value of the original function at negative 1? 1. So I'm right here, right? We know that already? If I draw a tangent line, do you all agree that the slope looks like this? I mean, that the line looks like that. What is the slope at that? What's the slope? Anyone know there? Melina? Any idea? This group right here, y'all got to get it. Y'all got to stop with the chatter and the talking because it distracts students who are paying attention. It either stops or you leave for good. Understand? I need you paying attention. So at negative 1, I'll give you one more opportunity. Do you know what the derivative is there, what the slope of this red line is? No? No? Anybody else? Close. I want the actual, that slope. It is connected to 2x, but what? I heard someone say it already. Negative 2. Negative 2. Why? Because if we're at 1, right, if our x value is 1, then to find the slope of there, what's happening there, we plug that negative 1 right here. Right? And so look at, if now we go down to this blue line, isn't the value of that point corresponding to the slope of that line? Yes? The value of that point is corresponding to that. So what if I pick another point over here? Anything I want. Like, let's say negative 2 this time. I come up here. The slope of that line Well, it's a negative slope, isn't it? Because it's pitched down like this, like left to right. But it's more of a slope than here, right? It's steeper, which means it should be a larger negative value, shouldn't it? Well, what is it? So we go out to -2, and we go down and down here, and it's -4. Yes? So what we need to make the connection here with is that the values of the blue function correspond to the slopes of the lines on the black function. I know it's weird, but that's fundamental here. What about at 0? Where's the tangent line at 0? It's flat, right? So it's a flat line like this. What's the slope of a flat line? 0. Well, guess what? What's the value of the blue function at 0? 0. See it? What happens if I pick a point over here on the black curve, like right there? That tangent line now has a slope that's what? Positive. Well, guess what? The blue one is now positive over here. Isn't it? And it would actually be, what? 2. Oh, no, sorry.
1.
This, at 1, right, at 1, the slope of this line would be 2. Sorry, 2. Because what's the blue function here? 2. I didn't draw, it doesn't look like 2 from the way I drew it. It should be a little steeper. It should be like that. Okay? Now, with that, I'm now going to draw an F. I'm going to draw an F. I'm not going to give you the function. I'm going to draw an F and ask you to draw the derivative. Or I'm going to help you, but do you understand the idea here? That these red lines dictate what the blue has to do. So let's do one of these. Okay. Students with this type of problem that I'm about to put on the board, it's usually like a light bulb goes off. It's like, got it. But until that light bulb goes off, it's like, what the hell's going on here? All right? So I'm hoping the light bulb will go off for everyone eventually here today with this. Okay, I'm going to draw a function, and then we're going to draw its derivative after that. So here's the function I'm going to draw. Let's see here. I'm going to put some points in here. -1, 1, 2, -2. These markers are terrible. Let me try this blue one over here. You know what? I think I have some in my bag. Nah. I don't know where the time goes. I hope that comes out okay. Can y'all see that enough? Yeah, I don't know if that's coming out on the camera. This is just to kind of guide you to let you know where those are happening. This is F. What does its derivative look like? All right, so the way you approach this is, first of all, let's look at some places here that we definitely know what the derivative is doing. So are there any places here where the tangent line is something very obvious to you? Okay, where? At the peak and then down here, right? Up there and down here? If I go up to this point right here, I think everyone would agree that the slope of the tangent line there would be 0. Yes? At -1, the slope of the tangent line is 0. So wouldn't that mean that the derivative at -1 would have to be 0? Isn't that what that means? So if I'm going to graph the derivative, that means I go to -1 and I put what? 0. So I just put a dot there, right? That red dot is the first point on my derivative that I know. The other place where this happens is here, yes? Here I have a tangent line that's flat, which means that the slope is 0, which means that the derivative, when I graph it at the value, x value of 1, should also be 0. So at x value of 1, my derivative is 0. So when I graph it, 0. Understand? Any other points that look obvious to you? At the origin, the slope of the tangent line looks like it's like something like this, maybe -1, right? So if I take the tangent line here, maybe it's -1 slope, which means that the derivative at 0 would have to be -1. So I would put that point where? I don't know, down -1, something like this. You following? Yes.
I don't understand how you can tell like that.
I can't tell how far it is. I can't tell how steep it is.
Like the 0 equals -1, like the actual slope, because you're pointing the slope down from 0.
This tangent line, do you agree that this tangent line is negative slope?
Yeah, dude.
And I'm guessing it's around -1. It's definitely not -10. It's definitely like not -0.1. Remember slopes, right? 0 slope, you're looking at me. So 0 slope, positive slope, that would be a slope of 1, right? Slope of 2, 3, 4, 5, 6, 7, 8, 9, 10. Vertical slopes are undefined. So the bigger the slope is, the steeper it gets. Infinite slope is straight up and down. So like a slope of 1,000,000 would still almost be vertical. Yes? Negative slopes, this would be very, very shallow negative slope, like 0.1, -0.1, -1, -2, -3, -4, -5, 6, 7, 8, got it?
Okay.
So what I'm saying is that right here, that slope, to me, looks like it's about -1. So on my derivative, I went down -1.
Okay.
If you did this, that'd be okay. Because we're eyeballing it. All right, does that clarify that? Okay. Now, over here where we had this interesting point, what can you tell me about the slope of the tangent line here? Positive or negative? Positive, right? How about the slope of the tangent line here? Positive. But what? This was positive right here, but steeper, which means bigger positive, right? And then what about the slope of the tangent line over here? Steeper again, but still positive. That means that as I move out this way on the derivative, all my answers should be positive, shouldn't they? And they should get bigger positive as I go, which means that my derivative is going to look something like this. So this point right here is a positive number, right? And I would say it's about whatever that slope is. I'm eyeballing this. And then, Melina, what's going on? You're just like totally zoned out. I mean, everyone in here is looking at what I'm doing and like, you're the only one who's just staring into space. If you're having a bad day, that's fine, but I'm just concerned. Here, right? Slope of the tangent line is what? Positive, but steeper, so bigger positive. So that's why I put this point up here. It's a bigger positive number, right? What about on the other side of this? What about right here? What's the slope of the tangent line here? It's negative. Small negative number, right? But as I move across, it's going to get, what, steeper, 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 until I get to what? That looked like -1, didn't it? So that means as I move across here, it starts out as small negative numbers, gets to -1, but what happens once I get here? Because I was this steep, right? What happens when I move out to like here? Is it still as steep? What's happening? It's shallow again, right? It's flattening out, going back to 0. So let's see if you follow this. When I started here, I had small negative numbers. They got bigger and bigger and bigger and bigger until I got to here. And then they started still negative, but now they're getting smaller negative numbers and back to 0. Then I move here, and my derivatives are what? Now they're positive again. Small positive, big positive, big positive, big positive, big positive. And so these numbers on the derivative are small positive, but getting bigger positive, bigger positive, bigger, and bigger, and bigger. And I'm done. Okay, that's the first time I've looked out, and everyone looks pretty like, okay. Like I said, the light bulb's got to go off. So does anyone feel like the light bulb kind of flickered there and you're good? Okay. It's going to take some time. We should do another one.
So the tangent line's going to be positive. You always see a graph going this way.
That's right. You always read these things left to right. So let me run through the blue one again. Right here, tell me about the slope of this line. Big positive, right? Big positive. So I go and I just, somewhere here at this x value, on my derivative, I just need a big positive number, which was up here. But as I move to the right, even though I have big positive numbers, they're getting smaller positive, right? They're all still positive, but they're getting smaller. So as I move across and I'm plotting points on the derivative, these are smaller and smaller positive numbers until I get to, what, 0? Now they become what? Negative numbers, but they're getting bigger and bigger and bigger until I get to here. And then it starts turning back. See, so there's still negative slope, but they're getting closer and closer to 0. And then positive numbers, and it gets steeper, so they get bigger. Again, it's one of those things where it's like, I see, or you don't, and then you just keep looking until the light bulb finally goes, and sometimes it doesn't ever go.
So if that was like a full sine function, like it continued forever,
Oh,
would its derivative be
absolutely.
cosine?
Awesome, yes. Let's look at the cosine sine function. That's great. We'll learn that later, that the derivative of sine is cosine. I'm not going to ask if you knew that, if you really knew that or not. But if you didn't know that and you made that connection, can't remember a student that's ever done that. I don't think I've ever had a Cal 1 student that ever made that connection this quick. So that's good if you really did see that. That's the sine function, right? Okay, so take a look at what is the slope of the tangent line right there at the beginning? The slope is positive. It looks almost like 1, doesn't it? It actually is. Okay? All right, let's pick out the nice points. This point right here, what's the slope of tangent line here? 0, so that means I need 0 here. Here? 0. Here? 0. And so on and so forth, right? Now back to this. As I'm moving here, I said the slope was positive 1. As I move across, these derivatives are all positive, but they're getting closer and closer to what? 0. So they're all positive and they're getting closer and closer to 0. And then once I get there, what happens to them? They start getting negative and they get closer and closer, still negative, right? Small negative to negative 1, right around there. So it goes like this to negative 1. And then once I get here and I start moving, they're still negative, but what? They're getting shallower and shallower, so it goes back to what? 0. And then what? I'm here now, right? Coming here, small positives until I get to what? 1 right there? Small positives, and then I start getting bigger until I get to 1. And then, where am I here? Small positives until I get back to 0. And that's cosine. So we'll find that later. We don't know that yet, but the derivative of sine of x is cosine x. Is the derivative of cosine sine? That wouldn't work. So imagine that the red one, forget the black one's here. What's the slope of the tangent line here? 0. Okay, so that looks like sine. But then what's the slope immediately start? Negative, right? So when I start drawing the derivative of the red one, it's going to be down here. That's not sine. But guess what it turns out to be? Negative sine. It's sine flipped over. Not inverse, just flipped. All right, let's get back to the notes. Or do we need more pictures? I don't know. I think what I'm going to do is let you suffer through problem 3. Is problem 3 on the homework for this section? 2.2. Is it there? Where's the folder? Oh, there it is. Number 3 is there?
Yes.
So number 3 is a matching problem where they give you the graph and they give you a bunch of graphs and they give you a bunch of derivatives. And you're supposed to match which graph goes with which derivative. That's a great problem to get kind of this idea down. Here's something else, though, I should at least warn you of. There are places that you have problems with derivatives. Let's say you had a function that did this. Or you had a function that did, I'm just going to put it over here, this. At these 2 points, here and here, your derivative does not exist. Remember, the derivative is a limit, right? The derivative is a limit. All limits require that as you come in from both sides, they're approaching the same sort of thing. So tell me about, what's the slope of the tangent line here? All positive, what? Positive 1? Yes. Let's say positive 1. So if I were to be graphing the derivative of this black one on this curve, it would look like this. Positive 1, positive 1, positive 1, until I get to what? That point? What happens at that point? All of a sudden, well, but it's only 1 point. See, it doesn't smoothly go over, does it? As soon as I'm at that point, what about right on the other side of that point? What is it? It flips to this, right? So the derivative is now at -1, isn't it? And it goes like that. So you see that the derivative, if I graph that derivative, see how the derivative is broken? That means the derivative does not exist. The derivative does not exist at this point because the derivative jumps when you graph it. So anytime you have a corner or what we call a cusp, your derivative does not exist at that point. It exists everywhere else. So this is actually a pretty interesting result. Is this black function continuous? Yes, it's continuous. But the derivative does not exist at a single point. There's a point at which the derivative doesn't exist. And this was a big problem for mathematicians. I don't know how long they were attacking this, but there was, these mathematicians were like, I wonder if there is a function that is continuous but nowhere differentiable, which means that you can draw it without picking up your pencil, but nowhere can you take the derivative. And it took a long time, but they found one. It's called the Weierstrass function, and it looks like this. Okay, so take that function. Where does that function not have derivatives? At all these corners, right? But then you would say, okay, well in here it's fine, right? Well, the thing about this function is that if you were to actually zoom in on this and zoom into that, that line would actually look like this. Like a saw blade. And so it would have discontinuities at a bunch of places, right? And then if you go and you look at one of those and zoom in on that, that one piece looks like that also. And then you zoom in on any one of these and it looks like that also. And it does that infinitely many as far as you ever go, so it's always got jagged edges. It's infinitely many fine-tooth function.
Do you know what that function is?
You can look it up on YouTube. It's an infinite summation of sine and cosine functions. But it's called the Weierstrass, Weistraus, something like that. All right, let's get back to these notes. Run out of time. So here's a function. I'm going to show its derivative, okay? Here we go. What should the derivative, if I start to draw that derivative from left to right, what should the derivative start out as? Negative or positive? Positive. Positive, because the slope of the tangent line is positive. So it should be positive, and it should eventually come in and flatten out to what? 0. So it's going to be, it's coming. There's the derivative, right? Positive numbers, look at the slope there. I have it computing the slope for me here. So you see I've got really, really steep, large values of the derivative, and then it eventually flattens out to 0, and then positive stays positive, right? So when you look at the derivative, it was positive, but it went to 0, but then it stayed positive. It's a little parabola. Yes?
Is there always going to be a degree difference between the function and its derivative?
If it's a polynomial, yes. Absolutely. 1 over x. So look at the tangent line here. Whoa. Isn't it always negative? It's negative, negative. Negative 1, somewhere around here. Really steep negative, right? So it's always going to be negative. It's going to be very small negative numbers. Very small negative numbers, and then it's going to get very big negative numbers. When I get to the other side, it's what? Very big negative numbers, but then they get smaller negative numbers. What does that graph look like? Well, it looks like that. The green one, very small negative numbers, very big negative numbers. Same thing on the other side. You're just going to have to mess with this. Okay, you're going to have to do that problem number 3 and try and make these connections. All right. Now, some notation. Since the derivative is so important, if we ever have a function y equals f of x, then there's so many different ways that someone can tell you that they want you to take a derivative. They can write f prime of x. You've already seen that, right? If they're calling the function y, then they can just write y prime. And they mean the same thing, take the derivative. They can use this notation, dy dx. This is called Leibniz notation right here. They can say df dx, which means take the derivative of the function f with respect to x. The x down here just tells you what the variable is in the problem. This right here, d over dx, is telling you take the derivative. X is your variable. Oh, the derivative of what? The function f of x. This is all notation, that's all it is. This capital D, f of x means take the derivative of f of x, capital D, right? That's what it means. This one, same exact thing. Take the derivative of the function f of x. Oh, and take the derivative, x is the variable. So these are all the same way of saying the same thing. Now that last notation looks like, well, why in the hell do you need all this notation, right? Because in Cal 3, you have functions of more than one variable. So you have a function of like x, y, and z. You have 3 variables in the problem. And this right here would tell you that you're going to be taking derivatives, and it would tell you what you're going to treat as variables, what you're not, and it would tell you what order to go in. So it would say, first take derivative with respect to x, treating x like a variable, then do it with y, and then do it with y. So the notations that are like, why do you need that, really come later. So we are going to focus primarily on these first, I'd say those first ones. I don't think I've ever used capital D on anything I've ever used in a Cal 1 class. So just be aware that there's notations. Some more just definitions. A function f is said to be differentiable at a point A if the derivative exists. Remember, the derivative is a limit. Some limits don't exist. So not everything's differentiable. A function f is said to be differentiable on an interval if the derivative exists at every point in that interval. If a function is differentiable at a point, it must be continuous at a point. This is a very strong theorem. Differentiability implies continuity. So if someone says, hey, look, I got a function and the derivative at 2 is 1, guaranteed it's continuous there. Guaranteed. Doesn't work the other way around. Just because you're continuous at a point doesn't mean you're differentiable. I gave you that example right there. That point right there, it's continuous, not differentiable. All right, so where do functions fail to be differentiable? At a corner or cusp, I showed you. Anytime you have a jump in a graph, if you have a function and it jumps, it's impossible to be differentiable at this jump. Can't happen. If you have a vertical tangent line, you have a problem with the derivative. Let me show you an example of a vertical tangent line. What about a function that does that? I want you to focus on the point right here. So talk about the slope of the tangent line. Small positives, getting bigger, getting bigger, getting bigger. Right here, what happens? It tries to go vertical, doesn't it? What's the slope of a vertical line? Infinity, undefined. It's possible. So what happens is at this point right here, it's impossible for us to define the slope. If the derivative is the slope, then we can't define the derivative. So you have infinite slope, no derivative. So anytime you have that, you've got a problem. And I showed you. There's the corner. And the issue was that it switches, right? The derivative immediately switches from a positive to a negative number. Here is the jump. So the derivative, see how it switched real quick? Same thing. And then the vertical tangent, what I just drew here, right? I think if I do it right, I can get my computer to freak out. Yeah, see infinity there for the blue? So, all right, so if I said that the derivative is a functional operator, it takes a function in and spits a new function out, right? Then can you send that new function back through the same operator? Right? So, like we took x squared. What was the derivative of x squared? 2x. Why not take the derivative of 2x now? That would be going backwards. It would be the derivative of whatever 2x is, which we haven't worked out. But there's nothing stopping you from applying the same thing. It's like, you know, you take a car through a car wash, right? You can take it through again. I mean, the car wash is there, right? So the derivative is an operator. It doesn't matter what you plug into it. So there's no problem in plugging functions in over and over. So if we do the derivative of a function one time, it's called the first derivative. If we do the derivative twice, it's called the second derivative. If we do it 3 times, it's called the third derivative. And we have different notations for each one. That little prime mark meant first derivative. 2 little prime marks means second derivative. 3 little prime marks means third derivative. And then after that, you're like, okay, the primes are getting kind of to be a pain in the butt, right? You wouldn't want to have like 17 prime marks for the 17th derivative. So what we do is we use this different notation. We use like f parenthesis 4 of x. That means the 4th derivative of the function. So you start out with the function, take the derivative once, get that answer, take derivative again, take that answer, do derivative again, that answer, do derivative again. 4 derivatives, you've got the 4th derivative. Got it? Be careful though, that is not the same as this. What's that mean? Raised to the 4th power, which is why we put it in parentheses. It's not because we just want to, it's because we have to distinguish it from this. This would just mean take that function times itself, times itself, times itself 4 times. This is derivative 4 times. Totally different operations. So 5th derivative, so on and so on. Now, if you want to use the other notation, Leibniz notation, it gets kind of complicated. The first derivative is dy dx. The second derivative is it looks like d squared y over dx, d squared y over dx squared. That's what you write if you want the second derivative. Why didn't they just do dy squared over dx squared like that to mean?
Because y is a variable, right?
Y is the function of x.
So then you'd be raising f of x instead of y.
You see that right away. See, you're thinking power now, aren't you?
That's why they don't write it that way.
They don't write it this way because you might think that this means like take the derivative and square it. That's not what you mean by that. What you mean is second derivative. So they offset the 2's so that you know that they're not talking about squaring anything. And then, of course, if you want the third, you just do the 3's offset, and then the 4th and 5th, and you can keep going. All right. Remember, we talked about position, function, that the derivative... Did we talk about this? Did we do linear displacement? No, right? No, we're thinking of something else. We've got 4 minutes. This might be a good place to stop. Let me see how much more. I think this is it, right? Yeah, this is it. Let me finish with this. I've got 4 minutes. So if you have a function, right? If you have a function, which we will call S, here's t, here's S of t. If this is position of an object versus time, so I know exactly where something is at every point in time, then the first derivative gives me the slope of the tangent line, right? And that would represent instantaneous velocity. That was the whole goal of this, right? This S prime is the instantaneous velocity. But we've just said that I can graph that, can't I? I can graph that derivative. So what if I graph the derivative then? Now, let's not get caught up in what it would look like. It'd be something like, let me see. That's kind of what the derivative would look like, okay? That's the derivative. Then it would be time here, and this right here would be velocity, wouldn't it? Velocity. Over here, it was time and what? Distance. So if you start with time and distance, the derivative is distance over time. Distance over time was speed. Yes? So distance divided by time gave us the unit of this derivative, velocity. Over here, since we have a velocity curve and we can take another derivative, then what would the slope of the tangent line on this curve be? Well, that would be the second derivative, wouldn't it? So S double prime of t would be this line. But what does it represent? Well, if this was distance over time, that's velocity. What's velocity over time?
Acceleration.
It's acceleration. That's acceleration. Why is acceleration that? Distance over time is velocity, right? Distance over time is velocity. But if I take velocity, which is that, and divide it by time, then I have this, right? Isn't that distance over time squared? Time squared. Which is velocity? You've heard that, like, what is it? What is the acceleration of gravity? 9.8 meters per second, or per second squared. That's exactly what that is right there. 9.8 meters per second. So we can see that we're going to get acceleration by just realizing that the derivative always gives you this unit over this unit, which means that's velocity. And then in this new graph, it's velocity over time, so its derivative would be acceleration. So if I graph S double prime, I know I'm out of time. That's my acceleration versus time. And that's all that this note says. If you know the position of an object at every point in time, the first derivative is the velocity function, the second derivative is the acceleration function. Okay, I'm going to have to pick up kind of with that as we proceed through. But next class, we will We will continue, okay, because there's one more section that I do want to put on the test. All right, so we're not going to have the test on Monday, but you will have new material on Monday that won't be on the test on Wednesday, because I can't just stop and, you know, we're going to talk about 2.3. That'll be on the test. 2.4 will not. So we're going to cover 2 sections next time, 2.3 and 2.4, and talk about review. You want the review I had for you? I had this. Now look, this is not a complete review. This is a test review I gave a few semesters ago, and this doesn't even, I don't even think this has derivatives on it, but it's just something you can start to look at, right? Take some here. Y'all pass those back. I hope I have enough. Take those, pass those back. Yes.